Section 1.3 Classification of integrals. Consider the first order partial differential equation f of x, y, z, p, q equal to 0 and mark it as equation number 1. And suppose z is equal to capital F of x, y be the solution of this equation number 1. And if we consider this z equal to f of x, y be a surface in 3 dimension, that is, if consider z is equal to f of x, y as a surface in 3 dimension, surface in 3-dimensional space, then this solution is called the integral surface. That is, consider the first order PD f of x, y, z, p is equal to 0. And we suppose that z is equal to f of x, y be the solution of equation number 1. Usually we represent capital F of x, y as a solution of a PD. And if we consider this solution, this z equal to f of x, y as a surface in 3-dimensional space, then this solution z is equal to f of x, y is called the integral surface. So what is integral surface? Integral surface is basically a solution of a first order PDE. Then there are 3 types of integrals. First one is complete integral. Complete integral. Again, we consider first order PDE f of x, y, z, p, q is equal to 0. Mark it as equation number 1. Then we suppose that it has a 2-parameter family of solution. Z is equal to capital F of x, y and 2 parameters. So a and b, small a and b are 2 parameters. Suppose Z is equal to f of x, y be a 2-parameter family of solution. That is, we consider a PDE f of x, y, z, p is equal to 0, and we also consider a 2-parameter family z is equal to f of x, y, a, b, where a and b are 2 parameters. Where z equal to f of x, y, a, b, be a 2-parameter family of solution. Then this solution is said to be complete if the matrix F A, F X A, F Y A, F B, F X B, F Y B has rank 2. That is complete integral. We consider a first order PDE and we suppose z is equal to f of x, y, a, b be a 2-parameter family of solutions, and this 2-parameter family is said to be a complete said to be complete integral. Is said to be complete integral if the matrix FA, FXA, FIB, YA, FB, FXB, FYB has rank 2. And what is FA? FA means differentiate this solution F partially with respect to A, and FP is differentiate this F partially with respect to D, and of course FXA, FIB, FIA, FXB, FIB are also the partial derivatives. Now this is the complete integral. Now second kind of integral, general integral. General integral. Consider the first order PDE f of x, y, z, p, q is equal to 0 and mark it as equation number 1. And also consider z is equal to capital F of x, y, a, b. This is the two parameter family of solution. That is, we consider a first order PDE and mark it as case number 1. Then we consider a two parameter family of solution z is equal to f of x, y, a, b, where a and b are two parameters, and let b is equal to phi of a. That is, we consider this parameter b as a function of this parameter b as in terms of a. Then this solution, this two parameters of family of solution becomes z is equal to capital F of x, y, a, and we substitute b equal to phi of a. Now this set is the solution and which has only one parameter, and that is a. That is, we converted this two parameter family solution into a one parameter family solution. In other words, this is a subfamily of this two parameter family of solution. This f of x, y, a, phi of a is the subfamily of this this two parameter family of solution. Now to find the envelope of this one parameter family of solution, to find the envelope of z is equal to f of x, y, a, phi of a. To find the envelope of z is equal to f of x, y, a, phi of a, we have to eliminate. To find the envelope, we eliminate the parameter a from z is equal to f of x, y, a, phi of a equal to 0, and fa plus fb of phi dash of a equal to 0. Actually, this is a procedure. Our aim is we have to find the general integral. So we proceed as follows. Now we get a one parameter family of solution, that is f of x, y, a, phi of a. And our aim is to find the envelope of this equation. For that, we should eliminate the parameter A from this one parameter family, and from this fa plus fb phi dash of a is equal to 0. And what is fa? This fa is differentiate this one parameter family with respect to A, and fp is differentiate f with respect to b. And what is phi dash of a? Differentiate phi with respect to differentiate phi and put differentiate phi of a, that is phi dash of a. And in fact, by solving fa plus fb phi dash of a, we get from fa plus fb phi dash of a equal to 0, we will get a equal to a of x comma y. That is, we will get a equal to a of x comma y. That is, a is a function in terms of x and y. Now substitute this a in this equation, and that is, therefore z is equal to capital F of x, y. A is a of xy, then phi of a, that is phi of a of xy. That is, we substitute this a in this one parameter family of solution, and we will get z is equal to f of x by a of x phi of a of xy. And what is this phi? Phi is a function. If we choose phi as arbitrary, then the solution is called, this general solution is called general solution. That is, if we choose phi as arbitrary, then the solution is called general solution. And if we take a particular phi, then the solution is called particular solution. Is called a particular solution. That is, if we choose this phi as arbitrary, then the solution is called the general solution. And if we take a particular phi, and then the solution is called a particular solution. Lemma 1.3.1. Let z is equal to f of x y a be a one parameter family of solutions of f of x y z p is equal to 0. Then the envelope of this one parameter family, if it exists, is also a solution. That is, the lemma says we have a first order PDE f of x y z p is equal to 0, and its solution is z is equal to f of x y a, where a is the parameter. Here only one parameter. So this a, there is only one parameter. That's why it is called a one parameter family of solution. Then the envelope of this one parameter family. If this one parameter family has an envelope, then we have to show that that envelope is also a solution of this first order PDE. That's what we need to prove. we have f of x, y, z, p, q equal to 0 and mark it as equation number 1, and z is equal to capital F of x, y, a, b, and mark it as equation number 2, b, a, one parameter family of one parameter family of solution. To obtain the envelope of this one parameter family, we need to eliminate a, that is to obtain, this is a procedure to obtain the envelope of to obtain the envelope of this one parameter family of solution. We obtain we eliminate the parameter a from z is equal to f of x, y, a, and f a of x, y, a equal to 0. That is, if you want to find the envelope of this one parameter family of solution, that is if you want to find the envelope of this equation number 2, we need to eliminate the parameter a from this one parameter family and from this equation fa of x, y is equal to 0. What is fa of x, y say? We differentiate this capital F, that is the solution. We usually denote capital F for solution. This capital F with respect to a and equal to 0. From these two equations, we should eliminate a to find envelope. And from this equation, we can obtain a in terms of x and y. That is, from this equation, we can form a in terms of x and y. And substitute, and from 2 capital F is capital F of x comma y comma, and substitute a equal to a of xy in 2 xy a of x comma y. Now this is the envelope. This is the envelope of this equation number 2, and we denote it as g. Since there are only two variables x and y, of course g is a function with variables x comma y. That is, g of x comma y equal to f of x comma y comma a of xy be the envelope of equation 2. That is, we form an envelope for equation number 2. For that, we obtain a in terms of x and y, and we substitute this a in our equation number 2. So we get f of xy, a of xy, and this is the envelope of equation number 2, that is one parameter family, and we denote it as g of xy. Now our aim is we have to show this envelope also satisfies the given PDE equation number 1. Our aim is we have to prove this envelope also satisfies the given PDE. For that, now f is a function with variables x, y, and a. So this is x, y, and a. Clearly, a contains variables, or a is in terms of x and y. So a is in terms of x and y. And we know this f is equal to g. F is equal to g. Now differentiate f with respect to x. Differentiate this f with respect to x. That is dou by dou x of, differentiate this equation with respect to x. Dou by dou x of g equal to, by chain rule, this is dou f by dou x into dx by dx plus dou f by, since we consider partial derivative with respect to x, the next one is dou f by dou a, dou f by dou a into dou a by dou x. Dou g by dou x is gx. Gx is equal to, what is dou f by dou x, that is fx, and dx by dx is 1, plus this is fa, dou f by dou a is fa into ax. Since this g is the envelope, and we know from this statement, to obtain the envelope of this one parameter family of solution, we eliminate a from z is equal to f of xya and f a of xy a equal to 0. That is, since g is envelope, this fa should be 0. What I mean is that this fa should be 0 from this one, and mark it as equation number 3. Equation number, both these two equations as equation number 3. That is, from this equation number 3, this fa should be 0, which means fx plus 0 into ax equal to fx. That is, gx is equal to fx. Similarly, differentiate this equation with respect to y partially. That is, dou g by dou y equal to, for the same procedure, it will be dou f by dou y into dy by dy plus dou f by dou a into dou a by dou y, which is equal to fy plus fa into ay. Since this f is an envelope, this fa should be 0, that is this should be 0, so it will be fy plus 0 into ay is equal to fy. That is, we get gx is equal to fx from here, and gy is equal to fy, which implies that the partial derivatives of envelope are same as partial derivatives of envelope means gx and gy. And what is fx and fy? Fx and fy are the partial derivatives of solution. From these two, we can conclude that the partial derivatives of envelope is same as the partial derivative of solutions. The partial derivatives of envelope is equal to the partial derivatives of solution. Which implies the envelope also satisfies the PD equation number 1. Let me conclude from this, the partial derivatives of envelope also is same as the partial derivatives of fx, the partial derivatives of solution. From this, we can conclude that the envelope also satisfies the PD f of x, y, z, pq is equal to 0. That is, if this first order PD has an envelope, if this first one parameter family of solution has an envelope, then that envelope also will be a solution of the given PD, and hence the lemma. Next we consider third type of integral, singular integral. Third type of integral, singular integral. We have already seen two types of integral. First one is complete integral, then second one was general integral, and now this is singular integral. A singular integral is obtained by finding the envelope of two parameter family of solutions. Z is equal to f of x by a. That is, a singular integral is obtained by finding the envelope of two parameter family of solution. Z is equal to f of x by a b. Here a and b are two parameters. That is to find the singular integral eliminate the parameters a and b. Eliminate two parameters a and b between z is equal to f of x, y, a, b, comma f a of x, y, a, b equal to 0, f b of x, y, a, b equal to 0. What I mean is that if we want to find the singular integral, we just eliminate the two parameters a and b between the given solution, and from differentiate the solution with respect to a and it equate into 0, and differentiate the solution with respect to b and it equate into 0. From these three equations we can eliminate. By eliminating the two parameters a and b from these three equations, then we can form the singular integral. Lemma 1.3.2. The singular integral is also a solution. So we have the PDE f of x, y, z, p, q equal to 0, and mark it as equation number 1. And now we consider the two parameter family of solution. Z is equal to capital F of x, y, a, b, and mark it as equation number 2. Is the two parameter family of solution. To find the envelope of this two parameter family of solution, to find the envelope of equation 2, we have to eliminate a and b from z is equal to capital F of x, y, a, b, and f a of x, y, a, b equal to 0, f b of x, y, a, b equal to 0. And together with these three equations, I mark it as equation number 3. What I mean is that if you want to find the envelope of this two parameter family, we have to eliminate the two parameters a and b from these three equations. And by solving these two equations, f is equal to 0 and f b is equal to 0, we will get a equal to a of x comma y and b is equal to b of x comma y. That is, if we solve these two equations, f is equal to 0 and f is equal to 0, we will get a as in terms of x and y and b as in terms of x and y. And from this equation number 2, from equation 2, we substitute a equal to a of xy and b equal to b of xy. That is, f of x comma y comma a of xy b of xy, and I denote it as g, and of course J has variables x comma y, and this will be the envelope of equation 2. That is, now we just form an envelope for equation number 2, and that envelope is g of xy is equal to f of xy, and from this equation number 2, or we substitute a equal to a of xy, b is equal to b of xy in equation number 2, and this will be our envelope. Next, our aim is we have to prove this envelope also satisfies the given PDE. Our aim is to prove the envelope G also satisfies the PDE, that is equation number 1. This is our aim. For that, we have f, and we know that f is equal to our g, and f has variables x, y, a, b, and from this a is in terms of x and y, also b is in terms of x and y. Now differentiate this equation with respect to x. For that, we have to use chain rule, that is dou g by dou x equal to dou g by chain rule, dou g by dou x into dx by dx plus left hand side is dou g by dou x, and the right hand side is dou f by dou x into dx by dx plus dou f by dou a into dou a by dou x plus dou f by dou b into dou b by dou x, and this is fx plus this is fa into ax plus, and this will be fb into bx. And we know f is the envelope. Since f is envelope, this fa should be 0 because of equation number 3. Not only that, this fb should be 0. That is, if f is envelope, then by equation number 3, fa equal to 0 and fb is equal to 0. That is, this should be 0, this should be 0. So dou g by dou x, gx is equal to fx plus 0 into ax plus 0 into px is equal to, that is, gx is equal to fx. Then by the same procedure, differentiate this equation with respect to y, we will get g y equal to, this is fi plus fa into ay plus fb into by. Since fa and fb are 0, this will be gy is equal to fi. That is gx equal to fx and gy is equal to fi, which implies what is gx and what is gy. Gx and gy are the partial derivatives of envelope. And what is fx and fi? Fx and fi are the partial derivatives of the solution. This is, that is, the partial derivatives of envelope and partial derivatives of solutions are same, which means the envelope also satisfies the given PD, and which is the lemma. That is, the partial derivatives of envelope is same as envelopes are same as the partial derivatives of solution, which implies the which implies the envelope satisfies the given PDE, and hence the proof.